This video is on graphing rational functions. A rational function is a function in the form of f of x equals p of x over q of x, where p of x and q of x are polynomial functions. So it's basically a rational expression that has a polynomial in the numerator and a polynomial in the denominator. So for example, f of x equals x squared plus x minus 12 over x squared minus 4 is a rational function. Notice it has a trinomial in the numerator and a binomial in the denominator. When graphing a rational function, it's helpful to first identify several parts. First of all, the asymptotes. What are the horizontal, vertical, and oblique or slanted asymptotes of the graph? Are there any points of discontinuity? Are there any breaks in the graph? Is there anywhere that, for example, x cannot equal 4? And what are the x and the y intercepts of the graph? So to find a horizontal asymptote, we need to compare the degree of the numerator to the degree of the denominator. And to make it easier here, I'm going to refer to the degree of the numerator as m and the degree of the denominator as n. So if m is less than n, so if the degree of the numerator is less than the degree of the denominator, then the graph has a horizontal asymptote at the line y equals 0. If m is greater than n, so if the degree of the numerator is greater than the degree of the denominator, the graph does not have a horizontal asymptote. It doesn't have to have one as a reciprocal function did. If m is equal to n, in other words, if the degree of the numerator and the degree of the denominator are the same, then the graph has a horizontal asymptote at the line y equals a over b, where a and b are the leading coefficients of the numerator and the denominator respectively. So if the degree of the numerator is the same as the degree of the denominator, take a look at the leading coefficients, and your horizontal asymptote is going to be at y equals leading coefficient of the numerator over leading coefficient of the denominator. A vertical asymptote occurs at q of x equals 0. In other words, what value of x makes the denominator 0, as long as p of x and q of x have no common zeros. An oblique or a slant asymptote occurs when the degree of the numerator is 1 more than the degree of the denominator, or m minus n is equal to 1. The equation of the asymptote is going to be p of x divided by q of x with no remainder. So use synthetic division and divide p of x by q of x, and whatever equation you have left, that's going to be the equation of the slant asymptote. A point of discontinuity, or a hole in the graph, occurs when q of x is a factor of p of x. In other words, when the denominator is actually a factor of the numerator. X-intercepts occur when p of x is equal to 0, and y-intercepts occur when x is equal to 0. So let's take a look at a couple examples here. We need to graph each rational function without using our calculator. We want to state the asymptotes, vertical, horizontal, oblique, any points of discontinuity, the x and y intercepts, and the domain. Now realize that a rational function may not have all of these, so we'll go through each one and see what it has. So here we have f of x equals 2x squared plus 3 divided by x squared minus 9. Well, the first thing that I'm noticing is that my denominator can be factored into x plus 3, x minus 3. So I'm going to start with vertical asymptotes. So remember, vertical asymptotes, no matter whether it's reciprocal or rational function, are when the denominator is equal to 0. So I'm going to have vertical asymptotes at x equals 3 and x equals negative 3. So that's a little different, that we have two vertical asymptotes. That's also going to tell me that my domain is x cannot equal positive or negative 3. I'm noticing that the degree of the numerator is the same as the degree of the denominator. In other words, m is equal to n. Therefore, that means that I have a horizontal asymptote at the leading coefficient of the numerator divided by the leading coefficient of the denominator. So 2 over 1, or the line y equals 2. Since no part of the denominator is a factor of the numerator, I have no point of discontinuity. And because I cannot And because they are the same degree, it's not m minus n equals 1, I have no slant asymptote. Okay, I'm going to have an x-intercept. Let's go ahead and look at x-intercepts and y-intercepts. I'm going to have an x-intercept when the numerator is equal to 0. So 2x squared plus 3 equals 0. 2x squared equals negative 3. X squared equals negative 3 halves. I can't do that. That's going to give me an imaginary number, so that means that I have no x-intercept. And then I have a y-intercept when x is equal to 0. So let's go ahead and plug 0 into the equation for x. So 2 times 0 squared plus 3 over 0 squared minus 9 is going to give me, that goes away, 3 over negative 9, or a negative 1/3. All right, so there's a whole lot of information. Let's go ahead and draw some stuff on the graph here. So I'm going to start with my vertical asymptotes, because I like those. There's x equals 3. Here's x equals negative 3, so this looks really different from what we've graphed before. And then I had a horizontal asymptote at the line y equals 2. There's my horizontal asymptote. I have no x-intercepts, but I do have a y-intercept. So that's going to be the point 0, comma, negative 1/3, which is going to be a little bit hard to see, but it's going to be somewhere probably right about there. Okay, so now I need to graph this. So I know that part of my graph is actually going to be kind of in this region. I'm kind of seeing 6 different regions here. So I know part of my graph is going to be in this region down here, and I'm not entirely sure where the other is going to be. So let's go ahead and make a table of values. Actually, I'm probably going to need a couple tables of values here. Give myself a little more room. So let's see if we can figure out what's going on in this area here, so that I know that when x is 0, y is equal to negative 1/3. And this is actually one time when I will use my calculator not to graph the function, but to plug in some values. So when I plugged in 1, I got negative 5/8, which is not a fun number, but that's okay. When I plugged in 2, I got negative 2.2. And when I plugged in 2.5, I got a negative 5.6. When I plugged in negative 1, I also got a negative 5/8. When I plugged in negative 2, I also got a negative 2.2. And when I plugged in negative 2.5, I also got a negative 5.6. My table's a little sloppy there. So I'm seeing that there's some symmetry going on there. So let's go ahead and graph some of those points. So at 1 and negative 1, I have negative 5/8. So something like right there. At 2 and negative 2, I have negative 2.2. And at negative 2.5, notice I can't choose x equals 3 because that's actually an asymptote. I have negative 5.6, which is going to be about negative 5.5. So something right there. So part of this graph is going to look like this. And remember, since the lines x equals 3 and y equals 3 are asymptotes, the graph is going to approach that. Now I'd kind of like to know, so that's what's happening between x equals negative 3 and positive 3. I'd kind of like to know what's happening when x is greater than 3. So I'm going to go ahead and do another table here. Oops, I'm going to run out of room here. Don't think I gave myself enough space here. So I know that when x is positive or negative 3, it's undefined. So let's go ahead and try a positive and negative 3.5, because I have a feeling we're going to have some symmetry here, that I'm going to have something going on here and something going on up here. When I do that, I get 8.5, which is not going to fit on my graph, but that's okay. When x is positive or negative 4, I get 5. And when x is positive or negative 5, I get 3.3. So when x is 3.5, I get 8.5, so something way up here. When x is equal to positive and negative 4, I get 5. And when x is equal to positive negative 5, I get 3.3. So something right about there. And I probably could have done 6. Wait, did I do that right? Yeah. So then that's going to give me something that looks like this. And something that looks like this. And because that line y equals 2 is an asymptote, let's make our graph look asymptotic. Okay, so that's the graph of this rational function. Whole lot going on here, but actually identifying like your asymptotes and your intercepts really help kind of define where the graph is going to be. So not all rational functions are going to look like this one in particular, but this is one possibility. Let's take a look at one more example here, and I promise this one is actually a little bit easier. Here we have f of x equals x squared plus 2x minus 3 over x minus 1. First thing I'm noticing is that my numerator can be factored. So this is going to factor into an x plus 3 and an x minus 1. And this is really nice because I'm noticing that I have a common factor in the numerator and the denominator. So the x minus 1's actually cancel. So that means that I am going to have a point of discontinuity at x is equal to 1. And because that's the value that would make the denominator equal to 0. Then what I'm left with is the function f of x equals x plus 3. Or if that's a little confusing, let's think of that. That's basically just the line y equals x plus 3. So let's go ahead and graph that. So I have a y-intercept of 3. Okay, but one thing I do have to take into account, so that's not my complete rational function. Notice I have a point of discontinuity at x equals 1. So that means I need to get rid of this right here. And I'm going to actually have a hole in the graph right here at x equals 1. And it's going to look like that. My domain, therefore, is going to be x is not equal to 1, so all real numbers except x is not equal to 1. My x-intercept, this is a little bit easier. I can actually get this off of the graph, is at negative 3. My y-intercept is at positive 3, and actually that's my b, and y equals mx plus b. This does not have any horizontal or vertical asymptotes or a slant asymptote. Just a point of discontinuity at x equals 1. So this one was a little bit more straightforward. So in this video we took a look at graphing rational functions, and there are a whole lot of rules and a whole lot of things you need to be aware of to help determine what the graph is going to look like. So please, as you're graphing this, as you're working through some of the problems, make sure that you're going back and identifying where your vertical and horizontal asymptotes are. Do you have any slant asymptotes, any points of discontinuity? What are your x and y intercepts? And then using that information, make a table of values. And here we took a look at just what 2 graphs of rational functions can look like, but there are a lot of other possibilities.